stream here. Yes, I am the only mommy. TA is also get an evaluation, but she's not a formal TA. So here's the thing about Cassie. She's actually my RA for this semester, and as part of her duties, I asked her to do this. So she's an informal TA, which is why she doesn't have any formal questions. But if you'd like to make comments, either to me directly or through the evaluations, I'll be happy to pass those on. So while we're on the topic of, I guess, grades and points and whatnot, are there any questions about homework or concepts? I want to make sure I try and hit as much as possible on our last day together. No, no one wants to volunteer? No? Okay. Then I thought maybe we could do a little bit of review. Here's the Excel sheet that I put up from Tuesday. I cleaned it up a little bit so that we could refer back to it as needed. The idea of how do you know what's significant and do you have to ask for it or does the program give it to you automatically? All right, we're going to review the responses. Great. So this is the little thing I developed last time. The idea of stepping through models that are increasing in complexity. So as you add new terms, what you want to know is whether the model works as a whole, whether the new terms that you've contributed actually add to your level of prediction. So we start with empty model, right? Empty model has no predictors in it. That's what it means. So it represents all of the variability that there is to be had in an outcome. So your mean square error term or mean square residual in Stata, that's what tells you how much variance there is to be had. So variance, just backing up to the very beginning, the idea of how far off each person's outcome is from the mean for the sample. Square that, sum it up over everybody, divide by sample size minus 1. So that way it's capturing how much individual differences there are to be predicted. The value that you get is always going to be unit specific. So whether you're in dollars or degrees or years or whatever your variable is, the number will correspond to your units. But the empty model tells you your starting point. So how much variance is there to be predicted in the first place? Because we haven't predicted anything, R square is 0. So we haven't reduced the variability by including any information about the people with respect to their predictors. If we add one slope of some kind, so this could be the linear effect of a quantitative predictor, it could be the difference between two groups. Just shorthand here, predictor A. Let's say that predictor A results in an R square for the model that is 10%. What that means is that the residual variance went down by 10%. So we've explained or accounted for 10% of all the reasons why people had different outcomes from each other in the first place. And in this case, when you only have one slope in the model, the significance of that slope is the same as the significance of the model. The model is the slope. So you can get that same information in two different forms, in regular units as the t-value for the A slope. So the slope will have an estimate. If you divide that by its standard error, that works out to be a t. You can compare that t to the sampling distribution and figure out where yours is relative to what is necessary to be called significant. You get your p-value that goes with that. Alternatively, if you think about testing the significance of the R square that came from that single predictor, that is done with F. In this case, if you took that T for your single slope and squared it, that would be the F value for the model. So you can look in one of two places for the p-value for whether or not your slope is significant / is your model significant. They're one and the same. So in this one case, when your R square change is relative to 0, that's the same thing as R square relative to the empty model versus just R square period for the overall model. Okay, questions so far? All right. Then if I add one new term, so I add predictor B. Let's say that my R-square goes from 10% to 15%. So now the F for the model will tell me the average contribution of those two slopes and answer the question as to whether that 15%, that R-square, is significant. In other words, is the correlation between the y that's predicted by my two slopes and the real one, is that significantly greater than 0? That's R-square, the square of that correlation. But that doesn't tell me directly whether or not the new predictor has something unique to contribute. The answer to that lies in the t-value for that new predictor. So because I only changed the model, is it being recorded? I believe it is. Let me double check with that. Thank you. Yes, it is. Because I only changed the model by one term, I added one slope. The test of whether that one slope is significant is the same thing as the test as to whether the model got better with it in there. And better is indexed in terms of the difference in R-square. So R-square went up another 5% from 10 to 15. That would mean that the t-value for the new slope tells me if that R-square is significant. So up to this point, to try and determine whether or not your model is significant, meaning your R-square is different than 0 given by F, and whether each slope contributes uniquely, all of that information is provided to you by default by the program. It's in this case right here, when you've added more than one slope, that you would have to ask the program for an additional test that quantifies the effect of both new slopes. So anytime you're adding two terms at once, there's two instances of this in Homework 5. So Homework 5 is predicting graduate school ratings from motivation, from GRE scores on the old scale, both verbal and CLOPE. You get all the information about the contribution of that slope directly. In the second step, I asked you to add both effects of GRE, verbal and quant, at the same time. So the research question would be, to what extent do GRE scores uniquely contribute to graduate school ratings above and beyond motivation? So there's two variables that go into that, two slopes at the same time. So what I will get by default is an F for the model that tells me whether the overall R-square is significant. And that F is weighted per slope, per contribution. So let's say hypothetically that R-square went from 15% to 27%. The F for the model tells me whether that 27 is different than 0. To figure out the change in it relative to the other model, so the extra 12% that my two effects would have given me, that's something that you have to ask for. So that is another F, but it's focusing on the joint contribution of the two new slopes specifically. This is what's known as a multivariate wald test. So the code to be able to do that would be down here. It's the statement contrast in Sass or the statement test in Stata. And example 5 has exact versions of these, but the idea is that each statement contains only a reference to the new slopes. So in this case, C1 and C2, separated by a comma in Sass, and Stata does it a little bit differently. It sets each one equal to 0 within parentheses. That would give me the test of whether or not the change in R-square is significant as a function of those two slopes, their joint contribution, which takes into account not only how related each is uniquely, but also any common variance that they have and the extent to which that common variance also contributes to R-square. To get the change in R-square, by the way, this is the one time this semester that I'm asking you to do a manual calculation. That's it. Subtracting a two-digit number. I know, it's crazy. Could you get your software to spit that out for you? Probably, but it's not worth the effort that it would take to try and program it in. There are other routines that you can ask it to do. This is known as hierarchical regression, where you add slopes in layers. Those routines tend not to be as flexible with respect to asking for estimate statements for linear combinations and other things, and so it's not worth learning something new just for that. So if you wanted to figure out how to get the F for the model, if for whatever reason that wasn't given to you or you just wanted to understand, the statements where you list every single predictor that's in the model, that would generate the same F as what's already given for you by default. So these are specific examples of a more general idea that whenever you want to test the contribution of multiple slopes at the same time, that's some kind of F. If it's all the slopes, that's the F for the model. If it's just a subset, then that's something that you can ask for directly. So in your homework, something like this happens in between sections 2 and 3, when you're going from one slope to adding in 2 slopes for GRE scores. It happens again in the next section because in adding the differences across levels of fear as your ordinal 3-group variable, you're also adding in 2 slopes at the same time. So to answer the research question as to whether fear of statistics still matters after controlling for GRE scores and motivation, you have to lump those 2 slopes that get you to the mean differences across groups back together again. So it would be the same thing, just adding in the 2 new slopes for your test statement or your contrast statement. So that was the one last thing that we hadn't really talked about until this week. So any questions on that? Okay, do you want to finish out example 5? Would that be helpful? May as well. All right, let me get that one pulled up here. Here it is. So what we had done before, I'll zoom back up to the beginning here. So this is example 5. We are predicting cognition as a measure of crystallized intelligence in a fake sample of older adults. We're evaluating predictors of their chronological age, centered at 85, their level of grip strength, centered at 9 pounds per square inch, as well as their standing with respect to dementia diagnosis, where possibilities are no diagnosis ever, diagnosis but not yet, that's the future group, or one that they have already currently. We looked at descriptive statistics and correlations before. In terms of models, so this is starting on page 10, an empty model would look like this. So this is your baseline. In terms of prediction, this is the worst you can do because everybody is predicted to just have the mean as their outcome. So the residual variance in this model, which happens to be 120, that's all of the variability in cognition scores that we have. That's going to be the highest possible value that mean square residual can be. It's got to go down from here. The worst that could happen is that it stays the same. So R square is 0, meaning we haven't explained anything yet. We looked at linear and quadratic effects of age. So after entering in a linear effect of age by itself, the mean square error went down. It went down by the R square value of about 3%. Because the F value for the model is significant, that's telling you the same thing as the T value for age being significant. T squared is F in this case. So that means that age does contribute, that we have a better prediction for each person's cognition score after accounting for their age. More specifically, with a negative slope, that means that older people are predicted to do less well than younger people. We have some effect sizes here for that, and D or R units that I added. Added in quadratic age to see if there's a potential nonlinear effect of age. The mean square error stayed pretty much the same. So this F value right here is still in regards to the overall model R square. It doesn't tell me anything about whether adding in a quadratic effect of age helped. To get that specific information, I would go down to the quadratic effect of age, the result for its slope, and it is not significantly different than 0, meaning that if there was no quadratic slope in reality, I would see one this big about 58% of the time. So well within expected territory. So that means we probably don't need it. Did the same thing for grip strength. Again, looking at all of these in separate models so we can figure out what's related to what in the first place before putting them all together. Grip strength by itself accounted for about 6% of the variance, and the slope is positive and significant, meaning that people who are stronger have higher cognitive outcomes. Did the quadratic effect to see if there was a potential nonlinear effect of grip strength. And again, the F for the model doesn't tell me anything about whether that quadratic effects helped. To figure that out, I have to go down to its slope coefficient, and it's the same story as age. It has a non-significant effect, meaning we probably don't need it in the model. And that is where we left off. So, questions so far? Nope. Nope, I gave you practice with that in 4. This is designed sort of to walk you through like in life, like how you would proceed with an analysis when you have multiple possible predictors. You would want to know what the relationship is for each predictor with the outcome in isolation to figure out whether or not it's a linear relationship or a curvilinear, what it needs to look like before you start combining predictors within one model. So we're looking at bivariate associations right now, just like age with cognition, grip with cognition. Now we're going to do gender with cognition. Okay. Other questions? No? Okay. So gender is another instance in which, because there's only 2 gender groups in these fake data, there's only one slope that I need to get between them. So the intercept for this model is going to give me directly what the predicted mean is for the 0 group, which is men here given the way that I've coded it. To get to what the mean would be for women, it's a linear combination of the fixed intercept plus the fixed slope times the value for women, which is 1, which is here. And that means that the slope itself directly gives me the gender difference. So in the results here, it looks like gender is significantly related to cognition. And in binary data, the 0 group is your reference, and the slope tells you how far away the 1 group is from the 0 group. So the 1 group here is women. And because the slope is negative, the 1 group is lower than the 0 group, significantly so in this case. Looked at effect sizes for those. Same idea, but with one more group for dementia. So this coding scheme right here is what we started with in homework 4. I don't think I had you do it in homework 3. I'm trying to remember. Nope, it was homework 4. This is different than the coding scheme that I specified in homework 5. So I've had a number of questions about this. Let me revisit this coding scheme real quick here. Go up to Spss so you can see it a little bit clearer. So this right here is how I set up the variables. So I decided to make group 1, which is the no dementia group, my reference. That means that both of their predictor variables are coded 0. That's what makes it the reference. I decided to make variables that compared each other to the none group. So this makes sense if it were a nominal variable where you just have a bunch of groups and you have one reference and you want to know what each of these others would be. So for instance, this goes to 1 for the future group. The second one goes to 1 for the current group. So in asking for model implied effects, I have to know how I coded it in the first place to figure out what the code would look like. So the model implied means would be given right here, where the intercept contributes to each one, and the value that gets multiplied by the slope is whichever value you gave it when you coded it. So the future group gets a 1 only here, the current group gets a 1 only here. And that means that the differences of the none reference group versus each other are directly given as model slopes, but the difference of the non-reference groups has to be found as a linear combination. And so those values in the coding scheme are then duplicated down here. So what would it look like if I wanted to change my coding? Let me go back to Excel for a moment and add another tab, such as in your homework. So let's say that we have our fear groups, where 1 is low fear, 2 is moderate, and 3 is severe. So what I had asked you to do is create new variables that would represent low versus moderate and moderate versus severe. So if low is going to be my reference group for the model, they get a 0 in both places. To make low versus moderate, then I need to give moderate group a 1, and I need to give moderate a 0 in the other variable. To make this one moderate versus severe, I definitely need to put a 1 here. The question is what goes in this cell. Nope. So there's two choices, I would say. That's one of them. It's either 0 or 1. So here's the question. This variable, low versus moderate, doesn't care which one this is, because this other variable is going to distinguish it. But in order for this one to represent moderate versus severe, this does have to be 1 here, because this first column is going to distinguish low from the others, and then this second column steps up to pick up where that one left off to distinguish moderate from severe. If you put a 0 here instead, then what this column means has changed. It would then be low versus severe instead, because the two that are being lumped together are these two. And so then the role of this variable would be to separate those two lumps as opposed to these two lumps. So let me put both of these here at the same time. Let's do those two. So it looks like many of you did it this way in your homework instead of this way. So there's that one versus that one. Now, which one is more correct? Trick question. Does it matter? It matters that you know what you have, but otherwise you have 3 groups, you just need 2 slopes. So if you did it this way, the variables that you created have low as a common reference point, and the first one gives you the difference between low and moderate, and the second one gives you the difference between low and severe. That means that you would have to ask for the difference of moderate and severe as a linear combination, the same way that you did before. Low is always 0, yes. So if you did it this way instead, so the difference is just this one cell in terms of what it means, then moderate versus severe is given to you directly by the model. And that means you wouldn't have to ask for it as a separate linear combination. Had I asked for low versus severe, though, then you would still have to make a third linear combination. So in practice, so long as you know what you've made, so long as you can interpret the effects of these predictors, you can set it up however you'd like. This way, where you have one common reference group versus each of the others, lends itself more readily to nominal variables where there's not any kind of ordering. Whereas this way right here lends itself to ordinal variables where you might want to know what the difference is between each successive category. So I had an example of this at the end of lecture 4, an example 4, looking at ordinal happiness, where there were 5 categories. And so I created 4 slopes that looked at the successive differences between categories, because in that context, it doesn't make as much sense to jump across categories, although you could get that as a linear combination. So the -1 Cheryl would come into play in trying to get the missing contrast. So if I did M versus S as my linear combination, it would be that slope versus that one. In this one, the missing piece would look a little bit different. If it was low versus severe, would be the missing one over here. That would actually require ones in both places, because you have to get from low to moderate and then from moderate to severe to get the full difference between the two. So point being, so long as you know what you've done, there's no wrong way to set it up. So just a brief digression about coding schemes. All right, questions on that? Okay, then back to example, this one. So this is the original coding scheme that treats them as the low group or the none group versus each other. So even though this model has 2 slopes in it, I'm still thinking of this as bivariate, because what this model is capturing is the relationship between dementia group and cognition. It's just that it takes 2 slopes to fully capture the 3 possible groups and their differences for this one predictor variable. So this is an instance in which there's no way that I could just run a Pearson's correlation or any other kind of correlation and get this information. This is what's known as analysis of variance. So I have my model parameters here. So 27 would be the predicted cognition for the low group, or the none group. -5 is the difference from the none group going to the future group. So the future group is lower, significantly so. And the current group relative to the none group is also significantly lower. And the difference between them is, did I put it on here? Yeah, I don't think I got the estimate for this on here, but it's right here, down below, because I asked for it as part of the code. All right. So the very last model then tries to put them all together. So what we know so far is to what extent each individual predictor relates to cognition. We've learned that people who are older are significantly lower in cognition. People who have stronger grip strength were significantly higher. Women were significantly lower. And relative to the none group, each of the other groups was significantly lower. So that describes bivariate information. The question is, to what extent do those findings overlap? Is it still the case that older adults are scoring lower on this test even after you take into account their physical strength? Is it still the case that gender matters in this test after you take into account their physical strength or their age? So we're trying to put them all together into the same model to try and ascertain which predictors matter uniquely and which ones don't. So what generally happens is that when predictors are related to each other, their unique effects, when all combined in the same model, are much smaller than what they were bivariately. So the syntax for putting everything into the same model doesn't work any differently than what you're used to. You just list out all of the predictors that you want slopes for in Spss here. Analogously, all the predictors that you want slopes for with a comma at the end in Stata. The extra pieces here that are in the code, I'm asking for things that are not going to be provided by default in most cases. So this right here and this right here, these are the f-tests for the model. So they're redundant with what shows up by default. I wanted to show them to you just as an example of what it would look like. When you get into more advanced models, those sorts of general models tests are not always provided for you anymore, so it's good to know how to get them. So we don't actually need those, but if I ever needed to get them because of a difference in software, that's how I would do it. This one and this one. These are examples of f-tests that I have to ask for to get the joint contribution of 2 or more slopes. So in this context, I'm lumping back together the 2 slopes that differentiate my 3 dementia groups so that I can get an overall test of whether or not group matters. For those of you who have had analysis of variance in your classes before, this idea of whether or not there are any differences across groups is referred to as an omnibus main effect of group. Omnibus meaning overall. So those 2 slopes are all I need to get all 3 possible differences between my 3 groups. And so it sort of lumps everything back together again rather than looking at each pairwise group difference specifically. And then for the group specific differences, these 2 are already in the model, but I have them here for reference so that the results are easier to sort through. And this is the new one that I would need. And here's the -1 showing up again. It's one slope minus the other to get a difference between slopes. And that gives you your mean difference for the non-reference groups. And then the same thing down here. One extra piece of output that this is going to give in Stata, I added this thing, this p-core. p-core gives you partial and semi-partial correlations. It doesn't work the same as Spss in that you can't get them for slopes that are lumped together. I have some information on the slides about how to do that if you ever need to, and it will involve some hand calculations of sums of squares. But in Spss, this contrast statement will give you semi-partial correlations with it. So that problem, that need to do hand calculations is not really necessary. Okay, so questions on the code or the logic of what we're doing? No, we're good? Good, mostly good? Okay. So then looking through the output piece by piece, here's my model. So this is a test of whether the 5 slopes work together to create a significant prediction, to create a predicted outcome that is significantly related to the real one. And this F value essentially represents a per slope contribution test. So the slopes on the whole, sums of squares is the amount of information that they've captured working together. It's the difference for each person between the outcome y hat that is predicted by the model and just having the model predict the mean, like in the empty model. Square that, sum it, divide it by the number of slopes. So this mean square right here represents like a per slope amount of information that has been captured. Then we got to know what's left. So sums of squares error is all of the information that's still out there. It's the difference between each person's real outcome and the one predicted by the model. Square it, sum it, divide by the number of possible slopes you could still add. That's denominator degrees of freedom. So sums of squares error divided by denominator degrees of freedom is this mean square error 88, otherwise known as our friend residual variance. Mean square for the model divided by mean square for the residual gives us our f. So this f represents the joint test of the 5 slopes are in this model, and it's scaled to think about like per slope as a contribution. So that means that if you were to add a slope that didn't actually help anything, it wasn't significant, your f would go down because it's like an average contribution. So if you had 6 slopes that captured the same amount of information, then the per slope contribution would look lower because of the extra one that you don't need. What this f is testing directly is this r square value right here. What percent of the original variation in cognition is explained, accounted for, attributed to, pick your words, associated with these 5 predictors? And it works out to be 28%. Whether or not that 28% is significantly greater than 0 is told to us by this f right here. So the model f is the test of the model r square. If I were to take each person's predicted outcome and correlate it with their real one, square that, that's r square. So you can think of r square as either the proportion reduction in outcome variance because of your model, or the square of the correlation between your model predicted outcome and the real one. Then we get into effect sizes. So each predictor has individual sums of squares associated with it. By the way, this thing type 3, that is what you get by adding this option in Spss. It's not given to you in Stata, which is why the PR core is necessary afterwards. But what type 3 means is that these things are not in order. So the model is agnostic as to which came first. That's usually what you want. There's a type 1 that you would see occasionally. That's used if things have to be in a certain order in terms of controlling for. So each predictor has its own amount of information captured, and that translates into its own semi-partial eta square. So these 3 you can interpret directly. What semi-partial eta square is, that is the semi-partial correlation squared. More directly, it tells you how much of the r square is because of that predictor. So it's an effect size, how much the predictor contributes uniquely to the model. These ones we can't use in the same way. We have to lump them together to figure out the joint contribution of group, because those slopes only make sense when they're combined. They can't be treated as individual variables. The reason for that, if we go back to my table here, if I just put that variable in the model by itself, would it be low versus moderate? Is that what it would tell me? If I did not have this one in here. So this one's gone, and all I have is this. If you look at the pattern of numbers, does that tell me low versus moderate? 0, 1, 0? It lumps, by the zeros being the same, it's combining low and severe and contrasting that against moderate. Likewise, if I were to just have this one in, that's not low versus severe. That's low and moderate together versus severe. So they only have the meaning that they have when they're used in combination. And the program doesn't understand that. So it's trying to figure out what the semi-partial would be sort of on an individual predictor level, which is not how they're interpreted. So in order to get the combined contribution here, that I had to get a contrast statement for. And then it gives me a semi-partial eta square for that. So putting it together, the overall model has an R square of 27%. This number right here is telling me that that of that 27%, 18% of it is because of dementia group. So it's by far the biggest player in this equation, so to speak. The other ones, 2% or so each, give or take. And then for Stata folks, I'm showing the calculations that you would have to do to be able to get that same information as a side step. If we go down to the solution then, intercept, first line here, get a little bit bigger. There we go. What's an intercept, folks? Yes, gestures. Here, there we go. Yeah, I can't do spatial reasoning and mirror images. That's just not within my wheelhouse. But I think this is right. Yeah, it's the point where the x-axis x crosses the y-axis. But in this case, we have multiple x-axes to consider. So the reference point for the model, the you are here sign of my airport map, so to speak, the you are here sign of my data, 29 is the expected cognition for somebody who is age 85, who has 9 pounds of grip strength, who is a woman, and who does not have dementia. All of those things. Relative to that person, each of these is providing the marginal effect of its own variable. What that means is that this coefficient for age says what the expected difference is between people of different ages, regardless of grip, dementia, or gender. So for every year older you are, cognition is predicted to go down by 0.4, and that is significant. Likewise, for every pound stronger you are in the squeezy thingy, cognition is expected to go up by 0.6, and that is significant. But this benefit of being stronger is irrespective of how old you are, what gender you are, and what dementia group you are. So that's what I mean by marginal effects. This is my gender difference. Gender does still matter after controlling for age and strength. Women are still lower, and the future and current groups are still lower than the none group. So all of these things retained their original direction and levels of significance in this example. If you wanted to see to what extent the effects of these predictors changed as a function of each other, so for instance, what if you expected the effect of age to be different for men than it is for women? Maybe men get hit harder by aging and women are more resilient. Or maybe women get hit harder and men are more resilient. We take a vote? No? It's a hypothetical. But could I find that out? Could I find out whether or not the effect of age differs across men and women? I could. This model won't tell it to me. Do you know what I need to do to find that out? No? That is correct. We didn't get to talk about that. But I'm giving a shout out to the last couple weeks of this course last semester where things were normal and we got to leave the house and not held class on Zoom. And we got to talk about something called moderation via interaction terms. So on the course website for this semester is a link to last semester's course where we got a chance to talk about those kinds of ideas. You saw one example of this in quadratic effects, where you had one variable multiplied by itself as a model predictor. That's exactly what you would need to do in this case to find out if the effect of age was different for men versus women. You would add another predictor to the model, that is the multiplication of age and gender. So yes, um, does age matter differently for men versus women? Does grip matter differently for men versus women? Does being stronger matter more if you're older than if you're younger? Those kinds of questions, those are what's known as moderation, and they're answerable via interaction terms. So if you have some extra time or inclination, I would encourage you to check those out because a lot of research questions are phrased that way. When people talk about risk factors or protective factors, have you heard those phrases in your research? Those are interaction terms. So for instance, I had a friend that I helped analyze her dissertation data when we were in grad school, and she was looking at the extent to which forgiveness was a buffer for the effect of stress on it's a level of psoriasis, which is a skin condition that's thought to be exacerbated by stress. So the idea would be that more stress is bad for you. They're this way. It makes your condition more severe, but in people who are more forgiving, that relationship would be abated, lessened, right? Different slopes for different folks. So forgiveness would be a protective factor against the effects of stress. That's an interaction term. Likewise, a risk factor would be something like what makes stress even worse? I don't know, having multiple sets of children to take care of. How's that? Statistics. COVID. Yes. Zoom. Yes, also true. Yes. Is Zoom a risk factor? Quite possibly. But yes. Okay, so here's a hypothetical. Let's say that you are afraid of statistics to begin with. And how does that fear predict your final grade? Well, it may predict your final grade more when you're on Zoom because of COVID, right? Fear is more bad for you in this environment. That's an interaction term. Now, we don't have the control group that we would need to try and figure that out, right? We'd have to have people have their fear before COVID and their fear after, and potentially maybe have COVID and Zoom as manipulated factors. Like we'd all be on Zoom without COVID, and then we would not be on Zoom with COVID, which means we're all sick, so that's not good either. So, yeah, risk factors and protective factors, that kind of language, those are interaction terms, and that's what we didn't get to this semester. So each of these effects is not specific to any kind of person. That's the take home. So even though they're controlling for each other, they're each their unique effects after controlling for each predictor. We're assuming that they're the same for everybody. And that's a testable hypothesis by introducing interaction terms. All right, how are we doing? Cheers. Cheers is good. I agree. So I have effect sizes in several different units that I've calculated from the t-test statistics. So the SAS code that I added is to do that. So the last two columns are the effect sizes that I added in terms of Cohen's d units. Those are standardized mean differences. So those would probably make more sense to report for these last four. Whereas for the two quantitative predictors, I think the R's would probably make more sense. So in terms of like the total information that you're reporting about each variable, in practice, what you would want to have is each variable's estimate, its standard error, its p-value, and then some measure of effect size. And in chapter 2 of my book that I gave you as a reading for this section, there's several examples of tables in there that would show you what this would look like. And I tend to lump together in a table both the original model parameters as well as the linear combinations. That way you can see all the group means and all the group differences in one place. And so those tables work that way. The book doesn't have as much of a focus on effect sizes because that goes away in longitudinal data pretty quickly, at least in this form. But another thing that you could do is to ask for standardized slopes in Stata. It gives them to you as part of the same regress command, and that's the very last column out here. So standardized slopes are as if each variable were z-scored, so they're all on the same scale. And so these are in an R metric where 1 or -1 is the highest you can go. And just to show you that that would indeed be the case, here is the same model using those z-scores. You get the exact same, the coefficients then are the standardized versions that you get. And as always, here's an example of a results section and a table. There are a lot of different ways that you can report effect sizes. So this table has all of the ones that we've talked about in whatever form: standardized slopes, Cohen's d units, R units, semi-partial correlation, and then their squared versions. And you can see they don't quite agree. In particular, the R's and the semi-partial correlations are a little bit different, and the standardized slopes are a little bit different. So the world of effect size can be a little bit muddy, squishy, pick your term. It's important just to pick one and go with it. Or if you want to give more than one, that's fine, but make sure you tell them how you calculated it. So like it bugs me when I read people's grant proposals or papers and they say, I have an effect size of 0.4. That could be one of like 12 things. So you got to tell me how you got that. So your choices would be R or D computed from the t-values, standardized slopes, and semi-partial correlations, or their squared versions that directly map onto R-square contributions. Those are the ones that would be most common in this context. And so in practice, you would tend to provide descriptive statistics and bivariate correlations where possible. So this table here shows you an example of those things being combined across variables. Note that dementia is not in the table because that takes 2 parameters to show it. And then here is a paragraph that describes each of the separate models, and then a paragraph that describes the joint model where everything's together. Now I want to point out that this is not the end of the text. So the results sections that I gave you in your homework, as well as the results sections that go along with each example, just tell you the words that are traditionally used to describe statistical findings. They do not include any context or theory or storytelling as to why the reader should care. And that is the most important part. So whenever you're reporting the results of analysis, it should always be as answers to questions or as the conclusion to a story. Just reporting this doesn't tell the reader why they should care. And that's the part that is always going to be context specific. And I can't give you a ready template for that, but just keep that in the back of your mind. Like the things that I'm saying, for example, this analysis shows that age still matters after you control for blah, 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 blah. That might be one story that you're trying to tell. Or age could be someone else's control variable, covariate that they don't care about. And this could be the story about how dementia is still bad for you even after controlling for age and gender and grip strength, right? It's your story, but the way that you talk about why these things matter should be in relation to research questions as answers or storytelling is the way I think that. So, yeah, that's all I wanted to say about that. Questions on any of that stuff? It's an interaction term, or one or more interaction terms. So if I had age by gender, like literally age 85 star, and then the gender variable, That does two things at the same time. It allows the effective age to differ between genders, and it also simultaneously allows the difference between men and women to differ as a function of age. And you can do that for any combination of quantitative predictors or categorical predictors. They get special names sometimes as a function of what type of predictor it is, but you can fit them interaction terms for whatever. And the same rules would apply in terms of the number of slopes that it takes. So for instance, going back to this example right here, where I have two slopes to describe the differences between the three groups, if I wanted to know if the effects of age differed as a function of dementia group, then that would be an interaction term of age with each of these variables, because that would then give me a different effective age within each dementia group, as well as a different difference between groups as a function of age. Nope, no, it's just a set of interaction terms. So that would be examples 6 and 7. And then I think, is there an 8? I'm trying to remember. Yeah. It's the same procedure, just adding in interaction terms. I can, yeah, let me pull that up real quick. I've been logged out. Nope, not that one. I'm going to go to this website. All right, so let me find where I pointed you guys to. Yeah, the numbering is off because last year I had it went from lectures 1 to 6, and this year I went from 0 to 5, so that the numbers were the same as the assignments. So that's why they're one off. So yeah, the one from the fall. Yeah, so number 7, for instance, let me just pull this up. It's actually continuing with the same data set, the same variables. So, come back. There we go. So this is how to make predicted outcomes and plots to start with. This is the same model that we just finished with just the main effects. And here, stop. So for instance, the first variable that I added was an interaction between age and grip strength. There's nothing else that's new in terms of the commands. So it's still regress and stata with a hashtag to define an interaction term, the same way we did with the quadratic. In SAS, it's still a, what do you call it? Losing my mind here. Star, an asterisk. So right here in this. All the rest of the code are examples of getting what are known as simple slopes. They are slopes of predictors at specific levels of their interacting predictors. And those are linear combinations using estimates and lincoms. So the same exact idea that you already know, just with a little bit more math behind their creation, because you have to be able to figure out what the model says each slope is going to look like. So that's moderation analysis. Using just quantitative predictors in lecture and example 7, and adding in categorical predictors in 8. All right, other questions on moderation or otherwise? Okay. Then one last thing I wanted to tell you about. This is protection against reviewer 2. So more words to live by kind of thing. This is in our lecture 5, dealing with problematic reviewers. This is slide 23. A few more points just about this. So if you have predictors that are highly related to each other, at some point, some reviewer is going to ask you how you handled multicollinearity. That's a big word. That just means that your predictors are related to each other. So you will see this as collinearity or multicollinearity, sometimes with 2 L's and sometimes with 1 L. That is a problem that is not a problem. What happens is that to the extent that your predictors have more overlap, it's harder for the model to show each of their unique contributions. The standard errors will be higher for a predictor to the extent that it has more in common with the other predictors. Once upon a time, I think that caused problems for computers to try and figure out. That's not a thing anymore. So you may see references to these things like tolerance or variance inflation factors. That's not a problem. The results are what they are. The thing just to keep in mind is that just because predictors don't have unique contributions doesn't mean that the model doesn't necessarily work. It's just that the more they have in common, the harder it is to see what they contribute uniquely. There's nothing you can do about that, but it's not a problem that you can solve. The only thing to watch out for is singularity, and that is when there is complete overlap or redundancy. So for instance, if I had a scale that had 3 subscales, and I entered in all 3 subscales as predictors along with the total score, the model's going to blow up at that point because the total score is the sum of the 3 predictors. It's perfect. A few of you have run into this by accident in troubleshooting your homework already. So for your 3 fear groups, if you have 3 groups, how many slopes do you need? Remember, three fear groups, how many slopes? Just 2. What happens if you put in a third? Does it run? It does run, but it gives you an error message and it zeroes out the third one because it's redundant. You don't need it. So that's the only thing to watch for, is when you put in predictors that are perfectly created from each other. Then that's no good. Problematic participants is another one. So yeah, everyone's been doing that. You will see these words used to describe outliers. So people whose values are extreme with respect to X or Y, who may have a lot of pull on the regression line. In this case, for instance, B looks like it's an outlier, but it's not necessarily that different from like where the rest of the data would suggest you're going. Whereas like C out here, if this wasn't here, you might see the line shoved a little bit more positive. So influence is the problem. You may see well-meaning advice about critical values of these statistics by which you should dump people from your data set. Nope, tread carefully. The only situation in which I would recommend deleting outliers is if their values are implausible. Like you have a coding error or they're just unbelievable for some other reason. There is a technique that if you take the generalized class, you will learn about. For this situation where you're concerned about outliers, it is what's known as quantile regression. What it does is predict the sample median instead of the sample mean, and the median is much more robust to outliers. So quantile regression is a better alternative if you're worried about people who are pulling your regression line one way or the other. Another thing you may hear about is suppression. That's where the pattern of results are somewhat unexpected because of differences between the bivariate and unique relationships. So this can happen given these particular circumstances, such that the unique effect of a variable can actually be stronger than its bivariate effect. So I point this out because this is a thing that can happen to you. It doesn't mean you did something wrong. What it does mean is that if a variable is not related to an outcome bivariately, all by itself, doesn't necessarily mean it won't be related still in a model. It can happen that way. So be aware of that. Let's see here. Here's an example of an unexpected result where none of the predictors are related bivariately in this correlation matrix, yet they contribute to a significant model. That can happen, rarely. Another one is if you do have a significant bivariate relationship, but the model is non-significant. That's because the model is evaluated per predictor. So if you have a bunch of crap in there you don't need, the model looks like the R-square value is not significant. And you can have something like this. This is my favorite one. So this is Spss Output, by the way, that I borrowed from someone else. So we have predictors that are highly related to the outcome as well as to each other. But when you put them all in the same model, the significance column right here, the p-values, none are significant. Yet we have a significant R-square. So in this case, no predictor has a significant unique relationship, yet they work together to create an R-square of 20%. That can happen. All right, that's all I had to say about that. So, questions? There, beach screen. That's nice, much nicer to look at. Questions, comments? Sure, hit me. Great question. I'm not entirely sure of the answer, but I think it's not going to be for another 2 years. The good news is that any of the courses that I teach will live forever on the YouTube, so you can have access to the material whenever it's convenient. There are sections of that course that would be prerequisites for other courses, but if you went through those things on your own, you would probably still be in good shape to take future courses. So my regular rotation, this fall I'm teaching structural equation modeling, which with some review of the stuff that we didn't get to and the generalized stuff you would probably be able to do in the fall if you wanted to. I also teach classes on longitudinal modeling and multi-level modeling of people nested in groups. And so those are the sort of the 4 advanced classes that I rotate across, and I teach this every semester as it is currently. So yes. Yeah, the only official prerequisite for that class is, on the books at least, is intermediate statistics and correlation and regression. But we got through enough of that that I believe your preparation would be similar. There's just a few extra pieces that show up in structural equation models that aren't actually part of either of those classes that it would be good to see on your own ahead of time so that it's the second time you see it when you come through for that one. So, all right, sure. So I wanted to let you guys know that by surviving this semester, you have earned a lifetime pass to bother me. So if you want to do these things on your own and you find yourself getting stuck, or SAS or Stata is yelling at you in red and you're not sure why, please feel free to contact me and shoot me an email. I'm happy to help. It would make me actually really happy to know that you're using this stuff in your world. That would make my day. So please don't be strangers. Lifetime pass. No, I'm serious. My ultimate goal is to make myself unnecessary. That is my ultimate career goal, that everybody knows how to do this stuff as well as me, and so they don't need my help anymore. So this is my way to try and meet those career goals of mine. And I hope that you guys will, in the same, when you feel like you know what you're doing, turn around and help other people too and pay it forward. So, all right. In all seriousness, no, yes, not needing with statistics. No, we'll see about that. We'll see about that. I just want to say thank you to all of you. I know this has been unusual, and even in the best of circumstances, this material can be scary. And you stuck with it, and everyone's doing well. And I really am. I'm proud of you, and I'm grateful to you. So thank you guys for being there. Can we clap it out together? Silent clap. A round of applause for everybody for surviving. Yes. All right. So yes, I have office hours today. I have office hours all next week. Check on the webpage for the hours. And please let me know if I can help you now or later. And if not, enjoy your summers. And I hope you can stay the hell off Zoom sometime soon. Okay? All right. Bye, guys. Take care of yourselves.